Okay, so welcome to the next SIAM PDE seminar. This time we're pleased to host László Székelyhidi from University of Leipzig. Of course, for many of us, László doesn't need any introduction, but let me give a few words. So he received his doctorate degree in 2004 from Leipzig. After several postdocs, he landed back in Leipzig, although he held various good visiting positions, in particular in IIS last year. So László's interests lie in the PDEs in general, PDEs that arise in geometry and fluid dynamics. He's done major contributions to regularity theory of elliptic geometric PDEs and equations that arise in isometric immersion theory. Before given this groundbreaking idea of convex in implementing convex integration into fluids, in a series of papers with De Lelis, they introduced what has now developed into a very powerful tool, which led to the resolution of the hard part of the Onsager conjecture. And it just keeps giving, and there are more and more the sharp uniqueness energy conservation questions that have been resolved using the method. So for these efforts, of course, László has been honored with several awards. He received Oberwolfert Prize in 2010, ERC grant. He was an invited speaker at ICM in Seoul in 2014. He's got Leibniz Prize in 2018, and he also was a plenary speaker at the Congress of Mathematical Physics. So it's a pleasure to have him speak at the seminar today, and the title of the talk is on the screen: MHD Turbulence, Weak Solution in Conserved Quantities. László, please, the stage is yours.
Thank you very much, Roman, and thank you to Helena and all the organizers of this webinar for the invitation. I'm very honored. It's a very prestigious list of previous speakers. So I want to speak about magnetohydrodynamics. It's something that started to fascinate me in the last couple of years. I think it's a very rich system of equations and lots of interesting questions, and the results I will talk about is joint work with Dani Farako and Saul Lindberg. So what did I do? Just a second. Okay, so here is the system of PDE. This is a system of evolution equations for a velocity field U and a magnetic field B. And for simplicity, I will not have topology. I will just assume that we are on the in a periodic setting or in R3. The system consists of the momentum equations, which is basically the Navier-Stokes equations, incompressible Navier-Stokes equations, together with an external force, which is the Lorentz force induced by the magnetic field. So J here is the current. It's by Ampere's law. It's the rotation of the magnetic field, and so this is the momentum equation, the evolution of U, and the evolution of B is given by the Faraday part of the Maxwell system, which is coupled back to U via Ohm's law. So this is the electric field E, and E is given by the current times the resistivity minus U cross B. So with these additional definitions, this is a closed system of equations, which of course, if B is 0, reduces to the incompressible Navier-Stokes equations. And if U is 0, it reduces to the Faraday system. Okay, and so basically there are two small parameters: this nu, which is the viscosity, and eta, which is the resistivity, and both of them are assumed to be positive. This is the viscous resistive case, or the ideal MHD equations, which I will refer to later in this talk, is when both of them are 0. Okay, so plugging in the definition of the electric current and the electric field leads to this system, where you see here the Lorentz force as B dot grad B, so it has the same structure as the U dot grad U term in the Navier-Stokes system, and the evolution equation for B has this structure here, B, the curl of B cross U. And so I should just point out that this P pressure is not the same pressure as the previous pressure. I just didn't want to introduce a new notation. This is the total pressure, which includes the hydrodynamic part and also the magnetic part. So this is a rich system of equations with a number of conserved quantities. Some of them have analogues in the hydrodynamic case, others do not. So first of all, there's the total energy, which is the sum of the L2 norms of velocity and magnetic field. And second quantity is the cross-helicity, which is very similar. It's the scalar product of velocity and magnetic field. And the third known quantity is magnetic helicity, which is the scalar product of the magnetic field with its own vector potential. So A is the vector potential of the divergence-free field B. And these are conserved quantities in the sense that if you just formally differentiate them and use the equations, you get these identities. The rate of change of total energy is analogous to what you have in the Navier-Stokes equations, plus a similar term coming from the resistivity. The cross-helicity is again of the same order. It's one derivative of B cross product as a scalar product with one derivative of U. This is the current, and this is the vorticity. And the rate of change of helicity has this form. Okay, and so in particular, in the ideal MHD case, if these two small parameters nu and eta are set to be 0, then all of the right-hand sides are 0, and so all three quantities are formally preserved.
Could you tell me the physical meaning of the divergence free of A?
The physical meaning of A.
Why is A set to be divergence free?
Why it's divergence free? Yeah, it's a good point. So it's of course you could. It's a choice. You could set it to be.
It's a gauge,
additional
right?
Gradient. But this is usually if you have a domain with boundary or multiply connected domains, this plays a role. What gauge you use.
I see. It's the Coulomb gauge. I see.
It's a Coulomb gauge, exactly. So this is for the simple topology-less situation.
If you have a magnetic field, then I think it's natural to also introduce the electric field so that we can have them together. That's, I think, more naturally physical.
Could you repeat, please?
If you have a magnetic field, I think it's natural to introduce the electric field so that you can have both of them.
Yes, the electric field is E, which was in the previous slide here. This one? This is the electric field.
I see.
But the gauge by integration by parts will not change the definition of magnetic helicity. Okay, so let me just say just a few words about the magnetic helicity, because it's a very interesting quantity that includes some sort of topological information. So first of all, this is a quantity that is diffeomorphism invariant. The easiest way to see that is that you can write it in this form. Okay, so if you apply a volume-preserving diffeomorphism to your field, then it will not change the helicity, the magnetic helicity. The second point is that it's related to how the magnetic flux tubes are linked. So if you have, say, a magnetic field which is non-zero except in a small tube, then the magnetic helicity can be calculated as basically the linking number of these tubes times the flux in each tube. Okay. And so in general, the total helicity is the sum or asymptotic sum of these linking numbers. And there is a connection to the hydrodynamic case via the Kelvin circulation theorem. So Alfvén's theorem is what is referred to in the MHD case, is basically that the flux is the field lines are frozen in. So the magnetic field lines are being moved with the flow, the same way as vortex lines are being moved with the flow in the Euler equations. And so this is one way to write the B equation in the ideal case, which is basically nothing but the Lie advection of the divergence-free field B via U. Okay, so now in MHD turbulence, where these two small numbers nu and eta are going to zero, or the in the more proper way to say, the Reynolds numbers, the hydrodynamic and the magnetic Reynolds numbers are going to infinity, one observes a sort of relaxation phenomena in a sort of short time scale. The kinetic energy seems to dissipate, but on a much longer time scale, the magnetic field relaxes, subject to certain constraints. And so this graph is from a wonderful review by Yeats from 2020, which is just a numerical simulation of a toy model which was introduced by Moffat to indicate this sort of two-step relaxation process. The kinetic energy is going to zero very quickly, or almost zero, and the magnetic energy sort of seems to relax to some value. It's decreasing, but it's not so clear what is its limit. And so that's what is referred to as the Taylor relaxation theory. And so it's essentially an open question. What is the limit? So what the magnetic field relaxes to? Does it relax to the global minimum, subject to helicity conservation? This is what was proposed by Woltjer. Or does it converge to a local minimum? It's not so clear. So this minimization problem, you can already think about it without the evolution. So as I mentioned on the previous slide, Woltjer's minimization problem is to minimize the L2 norm of the magnetic field subject to helicity conservation. Okay, so this is what is observed, that helicity seems to be a very robust quantity. So we set that to be constant, it has a value, and then we just minimize over all L2 fields with that helicity. And Woltjer showed in the 1950s that the minima are given by what are called force-free fields. These are force-free because if the curl of B is parallel to B, then the Lorentz force is zero. They're also called Beltrami fields. Okay. Now,
and by helicity, what is it? Is it the helicity of which object? Is it the helicity of the fluid, or is it the helicity of the magnetic field?
This is the helicity of the magnetic field. And so far, there is no velocity. This is just simply a minimization problem, which was introduced by Woltjer in the context of this relaxation theory. Okay, it's just a first model, let's say. But of course, if you think about how in an ideal MHD situation the magnetic field evolves, it is transported by the flow of given by the velocity. This is the Lee advection interpretation of the Faraday system. And so Arnold, motivated by this, introduced another minimization problem, which is that you just minimize the L2 norm of a given initial magnetic field subject to being pushed forward by volume preserving diffeomorphisms. Okay, and it's not very difficult to see that this minimization problem will not give the global minimum in general. Okay, so even if the total helicity H is 0, in which case the Woltjer problem will give you the 0 field as the global minimum. Subhelicities, so you might have sort of two different linked tubes, and each one will have to be preserved. So even though the total helicity is 0, because the two linked pairs cancel each other, the total H is 0. Each one will have to be preserved by a volume preserving diffeomorphism. So in general, you will not be able to reach this 0 infimum. And there is a very interesting construction by Zakharov, Zeldovich, and by Friedman for the case where if you take the rotation field in the unit ball, then it is possible to reach the infimum 0 by a construction that basically is pretty singular, and it will involve so L2 norm of the magnetic field will go to 0, but the L infinity norm, for instance, will go to infinity. Okay, and there's a third, even more constrained relaxation problem, which is that you really look at the infinite time limit subject to ideal MHD. So ideal, sorry, I wrote ideal, but I meant a viscous irresistive MHD. So where the viscosity is positive, so it's Navier-Stokes, but it's irresistive. So helicity is preserved. Okay, that's another problem that one can consider, and I'm not really sure there is any result on this relaxation. Okay, so this is just to indicate that this is a complicated question, the Taylor relaxation. Now, on the other hand, these are two robust facts. First of all, that there is sort of anomalous dissipation of energy and cross-helicity. So there is an analogous zeroth law, analogous to hydrodynamic turbulence. So as viscosity and resistivity goes to 0, in the limit, the dissipation rate of energy and cross-helicity does not go to 0. That's the zeroth law. But at the same time, in the same limiting process, magnetic helicity remains essentially constant. Is there a question? Okay. And so this was pointed out, for instance, in the paper by Kaflish, Clapper, and Steele in 1997, that if in the ideal limit, where we set nu and eta to 0, we want to have a reasonable theory of weak solutions. These weak solutions have to basically reflect both of these properties. Magnetic helicity has to be preserved, but the solution should be weak enough that it allows for energy and cross-helicity dissipation. Okay. So the question is, what is a good theory of weak solutions? And it was proved only a few years ago that if you take sort of Leray-Hopf weak solutions of the viscous resistive MHD system, which are defined the same way as they are for the incompressible Navier-Stokes equations, in the inviscid irresistive limit, magnetic helicity will remain constant. Okay, so there is, even in this weak setting where the only thing you have is uniform energy bounds, the magnetic helicity is conserved in the limit, in this limiting process. Okay, now when looking at weak solutions, one sort of standard approach, which is motivated by how it works for the hydrodynamic case, is to look at some sort of averaging process. But rather than looking at random fields, one can look at sort of space-time averaging or just spatial averaging by some convolution kernel. And independent of what you do, you will end up with a sort of decomposition into mean flow or mean field and fluctuation. And the mean field will satisfy an equation that is similar to the original system, except it will introduce these additional terms. There is this Reynolds stress term coming from the effect of subscale terms to the macroscopic system. And the same way, there is a sort of what is called by Alloy and Eying subscale electromotive force, a sort of defect in the Faraday system, this Rm. Okay, and this comes from the effect of fluctuations to the macroscopic flow. And these were studied systematically by Alloy Eying and Greg subsequently also by himself. And they showed, for instance, that as the size of the convolution kernel goes to 0, even under very weak assumptions, this subscale electromotive force will go to 0 strongly in L1. So even under just energy L2 energy bounds. Okay, so it's, one might say it's maybe related to the Faraday-Lindbergh result, but I will come back to this in a few slides. So when discussing weak solutions of the ideal MHD system, one can just basically do it analogously to the Euler equations. So the energy space suffices because you just have these quadratic expressions inside the derivative. Whoops, yeah. So weak solutions or solutions in the sense of distributions make sense as soon as the fields are L2 integrable. And then one might ask the Onsager-type question: under what additional conditions on these weak solutions will the three quantities, the total energy, the cross-helicity, or the magnetic helicity, remain conserved quantities? Okay, and the rule of thumb in this type of calculation, which goes back to the work of Greg Eying and also Konstantin Öğen-Titi for the Euler equations, is to write down the formal equations of conservation in the local form. So you just multiply by u and b and put things under the derivative, and then just count. So in order to verify the conservation laws, you have to integrate. But then you have here, for instance, 3 terms of 3 copies of u and 1 derivative, which you can distribute on the 3 copies, and that leads to the Onsager 1/3. The same way here you have 2 copies of b, 1 copy of u. So it's again this Onsager 1/3, and the same with the cross-helicity. So you will obtain just from this and the sort of regularization argument, which goes back to, well, as I said, continuity in the context of Euler and also depend alliance for the transport equation, this result that if U and B are Euler continuous with exponent 1/3 or in this Biesov space, then the total energy and the cross-helicity are conserved. In the equation for the magnetic helicity, you see again there is here one derivative which you have to distribute on these three terms, but A has -1 derivative with respect to B. It's the potential. So one gains. This -1 derivative can cancel basically with this one derivative. And so the only thing remains is that you have to have L3 integrability. And this was a result proved by Kang and Lee. One way to...
But
Yes.
I think you already said that the helicity is a topological quantity. So what I understand is that the helicity does not change under like continuous or smooth operations like differentiation or
the
like
helicity does not change under applying a diffeomorphism.
Yes, so
but if you have a weak
quantity. Yes.
Sorry?
So yes, what I understand is that helicity is a topological quantity, right?
It's a topological quantity, yes.
Yeah, so it depends on the entire configuration of the solution. And what I think is that applying so-called analytic operations like differentiation and multiplication by another function does not really change the helicity. That's what I understand.
I don't know what you mean by applying any analytic operation. It's invariant if you apply a diffeomorphism.
Yes, that's what I mean.
If the magnetic field is flowing by a smooth vector field U, then the helicity is unchanged. But here I have a vector field U which is not smooth, so there is no diffeomorphism. It doesn't have.
Oh, I see.
So you see in this result by Kang and Lee, the vector field U is only L3. It doesn't make sense to think about its flow, its trajectories. So this is much weaker than you can't argue with the topological information.
I see. Thank you.
Okay, so you see. Okay, so this is maybe one indication of why magnetic helicity is so much more robust than energy and cross-helicity. So how far are these results optimal is like the other half of the Onsager conjecture. So there were a number of constructions of weak solutions of the ideal MHD system. Of course, the first observation is that if B is 0, then this reduces to the incompressible Euler system. So any result for the incompressible Euler system can be directly transferred. One more interesting construction was by Ambronsi, Milton, and Helena in 2015, where the velocity field is assumed to be horizontal and the magnetic field is vertical. So automatically U and B are perpendicular. And in this case, in this case, the B equation reduces to a passive scalar problem. So it's sort of like combining Euler with a passive scalar. And so in these cases, one has cross-helicity 0 automatically, and also the magnetic helicity is 0. Now, the first genuinely three-dimensional result was in 2020 by Beakey, Bookmaster, and Bicol, where they show that there are weak solutions in the energy space. U and B are in the energy space, that do not preserve any of the three quantities. Okay, so this is clearly, it lies below the Kang-Lee scaling. And so it's an example, but it doesn't get close to this L3 range. Okay, and the two results I want to talk about in this lecture are one so there are bounded weak solutions that do not preserve the energy and cross-helicity, but of course they have to preserve magnetic helicity. This is because of the Kang-Lee result. They are L3 because they're even bounded. Okay, but they are below this this Bessel regularity that is required for the conservation of energy and cross-helicity. And the second result is a sort of sharpening of the Beaky Bookmaster VCOL result, that there are weak solutions which are uniformly in this Lorentz space, which is just fails to be L3. So it's integrable with any exponent less than 3, but not in L3, that do not preserve the magnetic helicity, and also not the other two. Okay. So the technique in all of the results in the previous
let
slide.
me ask you,
Yes.
but is it weak L3? Is it exactly weak L3, or is it just anything below L3?
Yes, it's in the Lorentz Marcinkiewicz. I don't know what it's called. Is it Lorentz or Marcinkiewicz? I never know. But it's weak L3.
Weak L3. Okay.
Yes. Exactly. So, okay. So these results are all based on some form of convex integration. Now, in a nutshell, so convex integration is basically just a, let's say, a general term to describe iteration schemes where you have you construct a sequence of approximations UQ and BQ so the new terms are constructed by adding a highly oscillatory ansatz to the previous approximation. And so what this highly oscillatory ansatz has to satisfy, let me just briefly explain on the example of the Euler equations. So here, again, there is a sort of defect, which you should think of as the Reynolds stress term, but you can write any sort of error term in this way. And then the new perturbation, this W, is supposed to basically cancel on average this Reynolds stress term. Okay, so the new error at step q plus 1 should be given by the difference, the divergence of the difference of the W tensor W minus RQ. And there is a way to gain in this if the average of this term under the divergence is 0. And so basically, highly oscillatory means that the average of this term is 0, and the average induced stress is supposed to be R. Okay, that's a starting point of any type of convex integration construction. And then there's a lot of work in this gray part, but I'm not going to go into that in this talk. So one way to see more precisely what you need for this W is to imagine that this lambda is not fixed a priori, but it's something that you're free to choose at step Q. So you can sort of say UQ is given. I want to choose a W so that if lambda is sufficiently large, it gives a better approximation. So it's a little bit like homogenization. And so then what you see is that the average stress has to weakly converge to this previous one plus the Reynolds stress term. So that's the point. That is something that will follow from this condition here. And so somehow in any system, if you want to apply convex integration, you have to understand its its stability under weak convergence. Now, the typical result that one obtains then after this step and many other steps is something like this. So for the Euler equations, the statement will be that any vector field U bar which satisfies this sort of system with defect or system with the Reynolds stress term, if the stress term is positive, can be approximated by a sequence of solutions weakly. Okay, and the sequence of solutions, this uj will have kinetic energy that is basically the kinetic energy of the U bar plus the defect. Okay, this is what is referred to as an H principle type statement for the Euler equations. And I should mention that this result here is also true if you ask not just for bounded weak solutions, but Herder continuous weak solutions with exponent less than 1/3. This is what is referred to as the Onsager conjecture, which was finally resolved by Phil, I said, in 2018. Okay. Now, what about the weak stability or stability under weak convergence for the MHD system? The first observation is that already the Faraday system is weakly stable. And this is just basically the div-curl lemma for this system. So the div-curl lemma, now forget again about the U equation. This is just a question about a magnetic field B and electric field E. And the div-curl lemma of Tartar and Murat says in this case that if you have a sequence EJ weakly converging to E in LP prime and BJ converging to B in LP, the P and the P prime are Herder-Dual, then the scalar product of E times B will converge as a distribution. Okay, so this would, of course, in general, only if the EJ and BJ are solutions of the Faraday system. Otherwise, this would not be true. And the fact that this is not true is precisely what was important in the Euler case, that this U tensor U does not converge, I mean, the UJ tensor UJ does not converge to U tensor U, but it's U tensor U plus a defect. So this is a different phenomenon here. Let me just give a very quick proof of this, because I will need this formulation later. So one quick way of seeing this is to introduce what is I think sometimes in the literature called the Faraday 2 form, which is a 2 form in 4 dimensions. Space-time is 4-dimensional, built from the magnetic field B and the electric field E. And then the Faraday system, this system, F, is equivalent to saying that this 2 form is closed. Okay, in which case?
The omega, is it also called the field strength tensor, F mu nu?
I think so, yes. Yes.
Okay.
I'm not sure that there is just one name for this, but I found some reference where it's called the Faraday 2 form.
Okay.
Because it's the Faraday system. But of course, the Maxwell system has a differential form formulation as well, which is even more general.
Yes.
So in this case, this is just this closeness of this 2 form. And whereas the ideal Ohm's law, which is that E is the cross product of the magnetic field with the velocity field, just implies that E and B have to be perpendicular. And this perpendicularity amounts to saying that this 2 form is simple, meaning that that omega wedge omega is 0. Okay, because omega wedge omega is exactly this this scalar product. And okay, so the stability under weak convergence of this omega tensor omega can be seen by, excuse me, by the fact that you can just write it as an exterior derivative of alpha wedge omega. Okay, and so alpha wedge omega has better regularity because it has one less derivative, and so you can, the weak convergence is enough to pass to the limit in alpha wedge omega. Okay, that's the proof. Excuse me. Oops. Okay. And so the significance of this stability for helicity conservation is that this scalar product E dot B appears in the helicity conservation. Okay, so ddt of the helicity can be written as the integral of the scalar product. And so in particular, it's very easy to see that if you have any weak solution of the Faraday system with B in some LP and E in P prime, and you know that the scalar product, say pointwise, is 0, then helicity is conserved in time. Okay. So I just want to point out that in the Kang-Lee result, it is assumed that velocity and magnetic field are L3. Now, so B is L3, and E, which is B cross U, is then L3 half. So it falls precisely in this range of 3 and 3 half. Now, as far as sharpness of the exponents, this P and P prime, are concerned, here is one result that so given any say bounded reasonable, let's say piecewise constant weak solutions of the Faraday system for any P bigger than 3 half, we need this, otherwise this product doesn't even make sense. There exists a piecewise constant weak solution of the Faraday system B and E, which are in the weak LP and P prime spaces, so they just below being LP or P prime integrable, such that the product that pointwise almost everywhere is 0, and the helicity is given by the helicity of the original pair. But the original pair doesn't satisfy necessarily this orthogonality, so here helicity is not preserved. This is just an arbitrary electric field and magnetic field. Okay, so this way one can find solutions of the Faraday system which just fall below this integrability, and they are pointwise almost everywhere perpendicular, but helicity is not preserved. Okay. So the proof of this, let me just say in one word, this is really by something called the staircase laminate, which has been used in many PDEs as a tool for counterexamples which involve integrability. Basically, let's say in 2 dimensions, B is a rotated gradient and E is a gradient. So this B dot E can be thought of as like the determinant of a mapping in 2D. You can think of an analogy also in 3D, but let's focus just on 2D. And so in the 2D case, basically the question is, when does the area formula hold, or when can you define the pointwise? Sorry, when is the pointwise determinant of a mapping equal to the Jacobian? And it's exactly if it's L2 integrable. You can't do it below. So if you're below, it doesn't have to hold. This formula doesn't have to hold. And there's various. So this was proved, for instance, in this paper by Faraco, Moracoral, Oliva. There are other versions related to elliptic equations from previous work. And so there's a bunch of this type of statements. And so here again, it's about this sort of, when does the pointwise product give you something different from the distributional version? Okay. Okay, so coming back to MHD, based on this stability under weak convergence, this motivates a sort of relaxation of ideal MHD in the context of this Reynolds averaging, which will, on the one hand, involve a Reynolds stress tensor, like in the hydrodynamic case. So this is no different than what we have if B would be 0. But the Faraday system can't be relaxed as in the same way, because this electric field, this sort of coarse-grained electric field, has to remain perpendicular to B. Okay, at least if we are above this integrability range, but that's basically where magnetic helicity is preserved. Okay, if we are above this L3 integrability. Okay, so a way to say this in terms of this subscale electromotive force is that this force corresponds to Ohm's law given by a uniquely defined drift velocity. Okay, because it has to be perpendicular. Okay, so it's a partial relaxation. It's not just taking convex hulls, it's something more restrictive coming from this div-curl structure, this compensation structure. And once one realizes that this is the correct relaxation, which is consistent both with hydrodynamic closure, allowing for turbulence, and also with helicity conservation, one can start to think about how to construct weak solutions, which have to, at each step, satisfy these conditions. And this leads to the following statement, that for any weak solution of the Faraday system which satisfies this orthogonality, and any sort of, let's say, reasonable, some regularity assumptions, but this is technical, which can't be too small. These numbers shouldn't be, these functions shouldn't be too small. There are weak solutions of the MHD system which satisfy almost everywhere pointwise these relationships. And at the same time, the helicity is given by the helicity of the starting fields, the fields that we started with. So what's the point about making sure that these identities hold? Well, these are precisely the kinetic energies of the Elsesser variables. So in particular, the total energy plus cross-helicity would be this zeta plus, and the total energy minus cross-helicity would be given by the zeta minus. Okay, so this way one can construct weak solutions with given, in fact, pointwise. So this is sort of a version where one has energy density prescribed and cross-helicity density prescribed. Okay, but in particular, also the total energy and the cross-helicity is then prescribed, and at the same time, the magnetic helicity will not change from what it was at the starting field. And here we are forcing this orthogonality, but since I'm not saying anything about the integrability of this B bar and E bar, it applies also to the case with integrability below L3 and also for the case with integrability above L3. So maybe just one word. So this is maybe for people who have seen some convex integration before, the slide that is interesting. What one has to do is to construct sort of perturbations that are consistent with this additional nonlinearity, which is the new feature. This is not something that happens in Euler or active scalar systems. it's a sort of new feature. And the easiest way seems to be, that at least what we found, is to use these Clebsch variables. So basically you have given a solution which has a velocity field, some sort of stress field, which is the total of U tensor U, B tensor B, and Reynolds stress, and omega 0, which is the Faraday 2 form. We need to be able to perturb that in a certain direction by a sort of oscillatory perturbation, by a localized plane wave, let's say. And this localized plane wave has to have the additional property that the omega 0 was a simple 2 form, which corresponds to this orthogonality, and the omega also needs to be a simple 2 form. Okay, so that requires, at the end of the day, some sort of linear algebra calculation that is best done in these in Clebsch variables. Okay, so one corollary of this theorem is that you can prescribe the total energy, any continuous function of time, the total cross-helicity, they have to satisfy, and the magnetic helicity, which is a number, they have to satisfy some inequality, and then there are weak solutions which are bounded, and the total energy is given by this prescribed function E. The total cross-helicity is given by the prescribed function W, and the magnetic helicity is this prescribed scalar H. That's one result in the context of bounded weak solutions. And the second result is that there are weak solutions of MHD which just fail this L3 integrability. So they are in the weak L3 space, where neither of the three quantities is conserved in time. And so these are basically the structure of how these theorems 2 and 3 that I mentioned earlier are proved. So, of course, a big question remaining is how to move beyond this bounded weak solution setting to Beasov spaces or Höder continuous spaces. This seems to be very much inhibited by the fact that we have this nonlinear constraint. So I think this will require some new ideas. Okay, so that's it. Thank you very much for your attention.
Right. Well, thank you very much. So it's time to ask some questions. So there was a question that was asked earlier in question and answer section here by someone called Alexander. I don't see the full name. Mm-hmm. He's asking, what about the coupling between Navier-Stokes and Vlasov-Maxwell system?
Yeah, good question. I haven't thought about that, but but it makes in the context of plasma turbulence, that would be a natural question. I'm not really sure what to expect. I didn't think about that.
So any other questions from the audience? So, in classical turbulence, one of the features of a turbulent flow is what's called the locality of energy cascade, right? So when when the energy transfer from large scale to small scale in the forward direction, this transfer, the flux, is mostly controlled by the local scale. So I was wondering if these constructions that now you have this sharp convex integration construction, right, for the helicity non-conservation. I was wondering if you can also see the locality of the transfer in this context.
Locality in frequency.
In frequency, yes.
Yeah, I don't think so. Not yet. I mean,
because
so far,
it's sharp. It's already sharp.
No, you mean the one below L3?
Well, in weak L3.
The weak L3. Yeah, I mean, the frequency used in these perturbations is always huge. Mm-hmm. No derivative, not even a fractional derivative, is controlled. So it's just about the integrability. I think this is still way too weak to, these weak solutions are too weak to be able to speak about energy cascade. So I think, for instance, even in these bounded solutions, the energy spectrum would be extremely flat. There is no, I mean, you don't see a decay at all, because you just add stuff which is, I mean, it's decaying a little bit, but I mean, it's not any sort of fractional space better than bounded. So that's the challenge, how to get those type of weak solutions, if they even exist.
Elena, do you have a question?
László, thank you for a really nice talk. I was just wondering, do you foresee any kind of additional advantage to considering vanishing viscosity solutions, as far as going like supercritical or something?
I mean,
is there any
whether
physical
I see any
mechanism?
advantage to looking at vanishing viscosity solutions, and an advantage towards what goal?
To getting
I mean,
a supercritical.
I think that this result of Faraday-Lindbergh is very strong.
Okay.
That in the vanishing viscosity limit, magnetic helicity is conserved, because that only requires a L2 bound. Okay, it's just the energy bound.
Mm-hmm.
If you just take a weak solution of ideal MHD, L2 is not enough. That's the result. Oops, that's the result of Beaky Bookmaster Bicol. So this UB is in the energy space, but it doesn't conserve magnetic helicity. Okay, whereas the Faraday-Lindbergh result says that if UB is coming from, as a weak limit in the vanishing viscosity and resistivity, then H has to be preserved. In terms of bound, you will not get anything better than L infinity L2, right? It's the same space. So there is definitely an advantage from that perspective. I don't know if maybe this is what you're thinking about.
So it becomes a supercritical result in a sense, right? If you look at the vanishing
Yeah.
viscosity.
Yes.
Yeah.
I think it's a little bit like in 2D Euler, you have this type of thing. That vanishing viscosity will give you much better results than if you just take weak solutions in the energy space.
Yeah, you get Onsager supercritical results.
Yeah.
Vanishing viscosity.
Yeah, I guess that's what I was thinking.
Yeah.
Okay, thank you.